Good afternoon, everyone. I am pursuing MTech from MS University of Baroda. Today's our topic is radial flow turbine. The members in PPT are Parmar Dhonilsi and Parmar Aviraj. And my name is Parmar Aviraj, and I am starting the topics which is covered in this PPT. The first topic is introduction, second is elements of radial stage turbine, third is stage velocity triangle, fourth is enthalpy entropy diagram, and fifth is stage losses. First of all, introduction. In the radial stage of a turbo machine, the through flow of the fluid occurs mainly in radial direction, that is perpendicular to the axis of rotation. Therefore, the change of radius between the entry and exit of the stage is finite. This causes a finite change in the energy level of a fluid due to the centrifugal energy. The result is less mechanical stress and less thermal stress in case of hot working fluids, which enables a radial turbine to be simpler, more robust and more efficient in a similar power range when compared to axial turbines. The elements of radial turbines, as we can see in the figure, the first part is inward flow volute, the second is nozzle ring, then tip clearance, third one is casing, fourth one is exhaust diffuser, and then the exhaust takes place. In same the stage velocity triangle, nozzle blade ring and a high pressure gas inwards in the velocity triangle. When the high pressure working gas enters the turbine through a duct or pipe, an inward flow volute or scroll casing distributes it properly all around the nozzle ring or rotor blades. In some applications, the nozzle ring is not used as the flow receives some degree of acceleration accompanied by a static pressure drop in the volute casing. The rotor or impeller transfers energy from the fluid through the shaft through its blades. In a great majority of cases, the blades are an integral part of the rotor disc. While the flow has a large swivel component at the entry of the rotor, it is advantageous to allow only a small swivel component at the exit. In many designs, it is close to zero. If the kinetic energy at the rotor exit is high, a part of it can be recovered by passing the gas through an exhaust diffuser whose action is like that of a draught tube in hydro turbine. Some degree of swivel at the entry of the diffuser gives it a higher efficiency and pressure recovery. The second topic over is enthalpy entropy diagram. Figure shows the various flow processes occur in the IFR turbine stage on an enthalpy entropy diagram. The stagnation state of the gas at the nozzle entry is represented by point 0.01. The gas expands adiabatically in the nozzles from a pressure P1 to pressure P2 with an increase in its velocity from C1 to C2. Since this is an energy transformation process, the stagnation enthalpy remains constant, but the stagnation pressure decreases due to the losses. The equation is H1 plus half C1 square is equal to H2 is plus half C2 square. This is the figure of enthalpy entropy diagram, shows the variation of pressure. The isentropic process in the nozzle is represented by 1 to 2s, which does not suffer any stagnation pressure loss from this process. H1 plus half C1 square is equal to H2s plus half C2s square. The energy transfer accompanied by an energy transformation process 2 to 3 occurs in the rotor. Here the relative stagnation enthalpy does not remain constant on account of radius change. So the equation will be H02 relative is equal to H2 plus half W2 square and H03 relative is equal to H3 plus half W3 square. The corresponding pressure at the relative stagnation points are the relative stagnation pressures P02 relative and P03 relative. The final stagnation state is represented by point 0. Thus the equation will be H03 is equal to H3 plus half W3 square. The actual energy transfer work is equal to the change in the actual stagnation enthalpy. Therefore, using the general Euler's equation for turbine stages, which is WA equal to H02 minus H03 is equal to half C2 square minus C3 square plus half W3 square minus W2 square plus half U2 square minus U3 square. The further equation will be H02 minus half C2 square plus half W2 square minus half U2 square is equal to H03 minus half C3 square plus half W3 square minus half U3 square. H2 plus half W2 square minus half U2 square is equal to H3 plus half W3 square minus half U3 square. H02 relative minus half U2 square is equal to H03 relative minus half U3 square. Now the next topic is spouting velocity, which I am passed to our member Dhanil C. Parmar.
Hello, good afternoon everyone. I am Dhanil C. Parmar and rest of the topics are covered by me. The first one is spouting velocity, a reference velocity known as the isentropic velocity, spouting velocity or stage terminal velocity is defined as the velocity which will be obtained during an isentropic expansion of the gas between the entry and exit pressure of the stage. The exit pressure may be taken as P03 S is equal to P03 or P3, and which is also present in form of the equation as half C0 square is equal to H01 minus H03 isentropic. For a perfect gas, assuming that P03 isentropic is equal to P03, so we get this C0 is equal to under root 2 Cp T01 into 1 minus P03 by P01 raised to gamma minus 1 upon gamma. With the exit pressure equal to P3, half is equal to H01 minus H3 isentropic. So we get the final equation for the spouting velocity C0, which is under root 2 Cp T01 1 minus P3 by P01 raised to gamma minus 1 upon gamma. And the next topic is degree of reaction. The relative pressure or enthalpy drop in the nozzle and rotor blades are determined by the degree of the reaction of the stage, which is defined by the R is equal to static enthalpy drop in the rotor divided by stagnation enthalpy drop in the stage. There is a chart which shows the deflection of degree of reaction with respect to flow coefficient. We can see that the figure shows the plot of the stage loading coefficient with flow coefficient for various values of beta 2. Here the loading coefficient at a given flow coefficient decrease with the increase in air angle beta 2. It increase with the flow coefficient for beta 2 less than 90 and decrease with the increase in flow coefficient for beta 2 greater than 90. Then we will talk about the stage losses which occurs during the operation of radial turbine. The stage work is less than the isentropic stage enthalpy drop on account of aerodynamic losses in the stage. The actual output at the turbine shaft is equal to the stage work minus the losses due to the rotor disc and bearing friction. There are several types of stage losses. The first is skin friction and separation losses in the scroll and nozzle ring. The second one is skin friction and separation losses in the rotor blade channels. The third one skin friction and separation losses in the diffuser. The fourth one secondary losses. The fifth one shock or incidence losses, and the last one is tip clearance loss. So skin friction and separation losses in the scroll and nozzle ring. They depend on the geometry and the coefficient of skin friction of these components. Skin friction and separation losses in the rotor blade channels. These losses are also governed by the channel geometry, coefficient of skin friction, and the ratio of the relative velocities W3 by W2. In the 90-degree inward flow radial turbine stage, the losses occurring in the radial and axial section of the rotor are sometimes separately considered. The third one is skin friction and separation losses in the diffuser. These are mainly governed by the geometry of the diffuser and the rate of diffusion. The fourth, secondary losses. These are due to circulatory flows developing into the various flow passages are principally governed by the aerodynamics loading of the blades. The main parameters governing the losses are d2 by d2, d3 by d2 and hub tip ratio at the rotor exit. Shock or incidence losses. At off-design operation, there are additional losses in the nozzle and rotor blade rings on account of incidence at the leading edge of the blades. This loss is conventionally referred to as a shock loss, though it has nothing to do with the shock waves. And the last one is tip clearance loss. This is due to the flow over the rotor blade tips, which does not circulate to the energy transfer. And there is a diagram of losses in the rotor of an inward flow radial turbine typical curve, and we can see all the losses we have previously discussed in a graphical manner. Figure shows a typical plot of rotor losses against the incidence. The losses are minimum at the design point I equal to 0. Channel losses are nearly constant with varying incidence. Shock losses increase rapidly with incidence. Secondary loss constitutes a major portion of the total losses. The losses in an inward flow radial turbine stage can also be expressed in terms of nozzle and rotor loss coefficient as defined for axial stage. From the enthalpy entropy diagram, these coefficients are nozzle coefficient is equal to H2 minus H2S upon half C2 square, and the coefficient for the rotor is given as H3 minus H3S upon half W3 square, and all the parts are covered. Thank you.